Alright, welcome back to this YouTube channel again. So today we are going to be talking about some soft problems on plane waves in a conducting medium. This is a problem before us and we are asked to determine or calculate the following: propagation constants, the attenuation constants, and the others. These are our parameters that we were given. Don't forget, we can know what type of conducting medium this is if we look for this expression and check if our conductivity is far greater than omega times epsilon. If this is the case, then it is a good conductor. If our conductivity is much less than omega epsilon, then it is a good dielectric. But if our conductivity is approximately equal to omega epsilon, then it is a quasi-conductor, and I think this is the case we are going to be having in this question. So our complex propagation constant K, this our propagation constant, is going to be given by this expression, of which we can substitute here absolute permittivity to be relative permittivity times epsilon naught. So if we substitute in that part and we put every parameter here, we're going to end up having this as our gamma. So K should give us this. Don't forget, we have expanded this to be equal to this, and the square root of mu naught epsilon naught is always equals to 1 over the speed of light. So we have substituted that here. So if we put our parameters, this is going to give us the value for K, and now we can expand this using de Moivre's theorem. That's a complex number, so it is 1 minus j to the power of 1 over 2. So we can expand this by using complex number by first of all converting to a polar form and applying the de Moivre's theorem. So it's going to give us this value. So our final answer for K should be this. This is our required propagation constant. Our attenuation constant can be gotten from our K value. So this part is always our attenuation constant. So our skin depth, don't forget, for a perfect conductor, a good conductor, K arrow will be equal to Ki. In this case, our K arrow is different from our Ki because this is not a perfect conductor. So our skin depth is given as 1 over our attenuation constant. So we can still represent our attenuation constant by alpha. So 1 over our attenuation constant should give us our skin depth. So this is our expression for our wavelength of we are asked to calculate. Now let's write the expression for our intrinsic impedance. This is the expression for our intrinsic impedance, and don't forget, mu is mu arrow times mu naught, and also this is our complex permittivity. So if you substitute our complex permittivity here, we're going to have this expression. So we are going to walk around some steps there, which I did not put for the sake of the length of this video. So if we work on this using complex analysis, we are going to have this. So I've converted it back to the exponential form of complex number. So finally, our H field should be given by this expression. Don't forget, this is a relationship between the H field and the E field, whereby the intrinsic impedance is present. This is it. So if we substitute the intrinsic impedance here and do a little bit of arithmetics, we're going to have this expression. And finally, this expression here can be absorbed into this to give us our final answer for our H field as this. Okay, see you on the next class, on the next lecture. Thank you. So you can try this problem on your own to calculate the field intensity at a depth of 100 meters. This means that our Z is 100 meter. So we can calculate and substitute it directly.